experimental constraints on these kind of corrections from Newtonian gravity at short range. So again, there's this form here with this Yukawa type correction piece where you have some strength alpha relative to gravity, and then you have some length scale lambda that the force operates on. So the horizontal axis here is this length scale lambda microns, and here is the strength of the interaction relative to gravity. So the shaded area here is what's excluded by experiment, and some of the dotted areas here are some of the theoretical predictions from these high-energy physics models that suggest we find new ways in physics there. And so here, our experiment it has no sensitive limit at around the 10 micron length scale. There's another experiment at the University of Washington where we have better sensitivity at larger length scale, and at shorter length scales, the best constraints come from measurements of the Casimir effect. But so here, when we say we measured 100 times Newtonian gravity, that means if we were to extend our curve down here, we would see around 100 times gravity at sort of the length scale here, around 100 microns. But really, the interesting area is for our experiment is really more than 10 microns, where other experiments had not previously looked. Okay, so this is one example, and we're going to return to this again in the third talk when we discuss levitated spheres. But let me just give you for breadth, I'm going to give you another example of something that you can center. So one thing is magnetic resonance force microscopy. So here, the idea is you've got a solid with a single electron spin, and I've got a cantilever with a magnetic tip that I'm going to bring within a micron of that surface. And so there's some magnetic field that's emanating from this magnetic tip here, some static magnetic field. And then I have a microwave coil here, which I can use to drive, to apply RF here to drive oscillations in this spin. And so the idea here is that as this cantilever beam sweeps back and forth, the so-called resonant slice, where the Larmor frequency of the spin matches the mechanical resonance frequency here. So when the tip is in the correct position, then it's sitting in the correct magnetic field to be flipped by the RF from this magnetic coil. And so this is basically flipping the spin using an adiabatic rapid passage technique that's occurring at the motional frequency of the cantilever. So in this case, the cantilever is moving at kilohertz kind of rates, and the Rabi frequencies here are much higher than the coil. But so the sensitivity here is, in order to see this flipping spin, is really required at the atom level. So let's motivate that or go through that. So if I have a force from say the magnetic field from the spin acting on a moment on the cantilever tip, that force is given by the gradient of m.b, right? So if I've got a magnetic domain that's 100 in size, and I have say a magnetization per unit volume of say 10 to the 6 amps per meter, which is typical of say for a ferromagnet, then the moment here on the tip of my cantilever device is about 10 to the minus 15 joules per Tesla. So this is a pretty small magnetic moment. So to give you some scale, if I have a commercial squid, and I were to put some magnetic moment in the commercial squid, and I want to measure it, my sensitivity there is really at 10 to the minus 9 joule per Tesla. So this is about a factor of a million smaller than what your commercial squid can see. Okay, so I have this small magnetic domain on the tip, and now say I want to interact with a single Bohr magneton. So now the force is going to go like the gradient of the B field, so it's going to go like the distance in the dipole approximation, the distance to the fourth power times the magnetic moment here times the 4 magnetons times 4 pi. And so if I plug in a distance here of a couple hundred nanometers, then this force is at the additive level. So if I wanted to be able to measure force from the nuclear spin, which is a current goal in the community with the idea of doing high resolution NMR, then I need to be able to measure forces at the 10 to the minus 21. So this really motivates the need for this kind of sensitivities. And so in our, I'll just very briefly mention, so in our group we're also doing experiments where we're considering what happens if you replace this solid sample here with a trapped whole atomic gas? And so now we want to try to couple the spin of the whole atom to my magnetic calendar. In principle, I have the sensitivity to detect individual spins. And so the idea is that one might be able to do new things either in the context of quantum information or quantum simulation by using this mechanical device as a way of probing and manipulating the spins of a cold atom directly. And so this might have some applications, for example, high resolution addressing of atoms trapped in arrays. For example, optical glasses in a way that's not limited by optical diffraction. So the idea here is that you have a rubidium-87 atom. So here's the question.
Andy, may I ask you something about the last slide?
Sure.
So with the idea of measuring single atoms, so what would be the resolution that you would have? So say these atoms are in a lattice.
Yeah, so I mean, it's set by the tip gradient and the fabrication dimension, so it's kind of tens of nanometers.
How many?
Tens of nanometers. Okay, so the physics of the interaction is something like this. So you basically have imagine I have rubidium-87 atoms in some total magnetic field that's in part to the magnetic tip plus whatever sort of background electric field I'm applying. So in that magnetic field, this is the ground state hyperfine structure of rubidium-87. So I get a splitting here of the energy levels by h bar times the Larmor frequency. And so if I oscillate this cantilever now, such that the mechanical oscillation occurs at the Larmor frequency of the atom, that would drive transitions between the different Zeeman states in the atom, and this would couple directly to the atomic spin. And so we're setting up, we have an experiment now just to test some of the proof of principle. This idea is 1 megahertz cantilevers that are mounted on an atom chip where we collect rubidium atoms near the surface of the chip and then transfer them over to the cantilever for the experiments. So we don't have the results on it yet, but I just wanted to just quickly mention that. So anyway, back to the main part of the talk. So these are some examples of what some groups are doing with these kind of devices. And so now, how can we really push the sensitivity limit? And so here again, we looked at this formula and we found that we could make the cantilever small, we could lower the temperature, or we could raise the quality factor. So let's think about the quality factor. So in this case, of course, the Q factor is limited, as we've already heard now, several other talks. It's limited by things like clamping mechanisms. It's limited by surface imperfections. It's also limited by thermal materials loss, so there's thermal elastic dissipation and material flexes. And so by levitating the sensor now, I decouple this center of mass motion. If I replace this cantilever with a sphere and not to a trap, I decouple the center of mass motion very well from the environment. So I no longer have to be concerned with clamping, and also the materials loss is relevant if I'm just concerned with the center of mass displacement. So if I have a dielectric sphere, it has some polarizability in electric field laser. So the polarizability goes like the volume of the sphere, and then I have some optical potential, which is going to go like the polarizability times the electric field squared. So this is going to tend to confine the particle at the point of maximum intensity. Okay, so I'm got a little bit further than I expected, so I'm going to just maybe start a little bit into the second topic, and then we'll stop in about 10 minutes or so. Okay, so this leads us to the next subject, which is laser cooling and trapping of dielectric objects. So there's been a lot of work in the past decades on trapping atoms in vacuums, but not quite as much, except until recently, interest in trapping these larger size objects. And so I'll just say a little about the background and give you some more motivation, and then say a little bit about the details of how the trapping and cooling works, and discuss the limitations and some quantum effects. So as Oriel mentioned, this work really goes back to Bell Labs, so Art Ashman and co-workers in the 1970s, who were looking at trapping these particles, looking at trapping particles using light. And so this is the first result that was PRL in 1970 here. And so, so he has a sentence here, it's hypothesized that similar accelerations in traffic are possible with atoms and molecules using laser light-tuned specific optical transitions. Well, Ashkin, of course, later teamed up to work with Steve Chu, and Steve Chu Pride was kind of really seminal work, I think, for this field. So, and also, of course, it launched the area of optical tweezers, as William shows with a great video of biological objects attaching to spheres in solution. But so in vacuum, there had been much less work done. So in 1976, Ashkin had a result where he was able to levitate a sphere in high vacuum, and then for quite a long time, not a whole lot of work was really reported in literature. There was an example from a Japanese group in 97 where they were levitating in single beam tracking microspheres on the order of 1 to 2.5 micron radius. And then, of course, very recently, there's been a lot of interest in proposals, theoretical proposals, and experiments now for trying to get ground state cooling. And these systems aren't heard a bit about that. So this whole area has, of course, exploded in the past. There's probably 10 different view graphs just like this showing some of the progress over the past decade, but it's really exploded now that we've been able to get down to the quantum regime here, and these levitated systems in particular are particularly promising for getting to the ground state. So this is a proposal from Eric Chang and collaborators involving a sphere in an optical cavity with two light fields, so one light field to trap the sphere and the second light field to cool the sphere, and they show that principle ground state in the system. And there was also this really fantastic paper about trapping the living virus and superposition, putting the living virus in the superposition of states in trap. And so on the experimental side, Mark Raisin's group at UC Austin has a system where they've cooled in a dual beam optical dipole trap a sphere of 3 micron size down to the millikelvin regime, getting a quantity, getting around 3,000 or so quanta. And so here the idea is that you've got two beams coming in to balance the scattering force. We'll talk more in detail about the scattering force later. So we have two beams coming in to balance the scattering force, and we're holding on to this 3 micron sphere using an optical dipole force. So then they take some of the light out coming off of the sphere and basically image the plane of the sphere on some photodetectors. And so they can construct a basically a three-dimensional position measurement of the sphere by these tricks where they split the beam into two halves onto double photodiodes. So they measure the position of the sphere, and then they implement feedback cooling. So in all 3 directions, they have 3 beams at a different wavelength that are used to apply forces to the sphere to damp its motion. So the measurements of the position that are used using the trapping light are then phase shifted and sent to an AOM here to modulate the intensity of the cooling light in all 3 directions. So using the system they've got down to 3,000 quanta. There's a similar experiment, well, in some way similar, recently in Rochester, where here they did all the feedback cooling using a single beam, which was kind of a nice idea. So the idea is that they measured the position and then also its derivative, or its velocity, and looking at its product, they generated a signal at twice the frequency. And so they generated signals from all 3 axes here and summed them together, and then used that to feed back to the Popple cell to appropriately modulate the intensity to feedback cool this part of 3 dimensions. And they got down to Kelvin temperatures using a smaller sphere, in this case, it's something like 7 meters. And so these systems are really interesting for quantum applications because they're very well controlled environment. So So you have a very large Q factor, this is our maximum, this thermalization rate, KT over Q, is really low. And your excellent candidate for ground state cooling in these schemes where we cool the motion of an oscillator, the ratio of the initial to final Coulomb computation number is less than Q, so if I have a large Q to work with, originally this is the next handle for these systems. But so I'm going to, in particular, talk about how these levitated systems are useful as force detectors. And so here, so it's possible then to get into the regime, since I'm no longer limited by clamping the surface infection or materials loss, where I'm limited by collisions with the background gas. So if I look at how the momentum of the sphere is damped, there's some coefficient gamma which describes the damping due to gas, and that goes basically with the pressure of the gas divided by the RMS velocity of the gas times the radius of the sphere times the density of the sphere. So if you plug in some numbers for a respectable UHV environment, if you have 10 to the minus 10 torr, a sphere that's on the order of 0.2 microns, frequency around 100 kilohertz, this Q factor is something like 10 to the 12. So now let's take that Q factor and plug it into our formula here for the minimum detectable force. And so you'll see that even at room temperature, with a device like this, we can measure now 10 to the minus 21 newtons per meters. And so this is about a factor of 1,000 better than the state-of-the-art cantilever sensor. So I can also write this as, in this way, it's 4 kT times the gas damping coefficient times the mass of half. And I can plot how this sensitivity depends on the size of the object. So here's the radius of the sphere, the microns going down to 50 nanometers up to 10 microns, and this is the force sensitivity in newtons per hertz. So if I get down to smaller sizes, I'm below 10 to the minus 21 newtons per hertz. Even at micron sizes, it's still pretty impressive at the level of 10 to the, a few 10 to the 20. And if I put cantilever detectors on the scale, they're somewhere up here, 10 to the minus 18. And to be fair, I should also mention there was a result that came out a couple of years ago that demonstrated how trapped ions could be fantastic force sensors. And so they're actually coming in at a level even below what we're discussing. But the issue here is that now you have an ion, the ion is charged. And if you're trying to measure a force that's an electric field, that's fantastic. If you're trying to measure a force that isn't an electric field, it's kind of a big problem. Right? And so as an electric field sensor, this is fantastic, but for the kinds of measurements that we consider, it's not. So I can also cast this as an acceleration sensitivity, where now you can see that as an accelerometer for spheres that are a few micron size, you can get kind of nano G per root hertz acceleration sensitivity, which is already fairly impressive in terms of the state of the art. Okay, so maybe this is a good place to stop. So it turns out this picture here needs to be modified. It's not strictly applicable over the whole range of sizes of the sphere. In particular, when we take the size of the sphere to be much larger, this is going to change. We'll discuss that more on the next lecture. But this is probably a good start. So, questions.
So this is more of like a conceptual question, but if I want to measure a force, it seems to be relevant